Hello, everyone. My name is Marcy Samuelson, and I am Marketing Manager for the Developer Initiative here at Oracle. Thank you for attending today's webcast, Why Developers Choose NoSQL Database for Application Development. If you have any questions during the workshop, please put your question in the Q&A area, and we will answer your questions as soon as possible. We will have a live Q&A at the end of the webcast as well. This webcast is being recorded, and we will make it available shortly after the webcast concludes. Again, thank you for joining today. This webcast will be presented by Michael Bray, Director, NoSQL Product Management at Oracle. At this point, I will turn it over to Michael.
Thank you, Marcy. Hello, everyone. As Marcy said, my name is Mike Bray, and I am with the Oracle NoSQL team. So let's go ahead and launch into the discussion today. Here's our standard slide that we have to put up. I'll just leave it up here for a moment or two so everyone can take a look at it. So today we're going to really talk about three different things. What are some of the technical drivers behind the creation of the NoSQL technology? We're going to talk about use cases and various deployment patterns for NoSQL. And then interlaced with that, and a little bit toward the end of the presentation, we're going to cover design trade-offs that are commonly made by application developers when they really have to choose between a relational database and a non-relational database. So NoSQL databases are here to stay. You know, they're expected to take a fairly large market share going forward. In some research that I found from Allied Marketing Research in an April 2020 paper, they indicated that the global NoSQL market is expected to reach $22 billion by the end of 2026. And that's with a 31.4% compounded annual growth rate. That's a lot. You know, roughly 2.5 billion gigabytes of data is created each and every day, and businesses are struggling to keep up with this ever-growing demand for information. You know, a lot of this is getting stored in key value type databases. You know, and North America is expected to maintain the market share leadership over this time period. So what is NoSQL, or really more importantly, what it isn't, right? There's a lot of confusion in the market about what it is and what it is not. You know, here are a couple of points to think about. You know, even though SQL is in the name, it's not about the SQL language. While some NoSQL databases will use a SQL language, many of them really will use their own proprietary query language, and some of those are easier to understand than others. Although its genesis is probably in big data, NoSQL databases have grown well beyond big data environments. Some of them run in the cloud, some of them do not. Some of them are open source, some are closed source, some are a combination of both, right? They don't require any special hardware to run, and they really run their best on commodity hardware. You don't have to be a member of some exclusive club to use them, and they're probably not going to take over the world, right? They're not based upon complex mathematical formulas used in set theory. So what is this thing that we call NoSQL, right? NoSQL systems allow you to place your data into a table and then query it without ever having had to create some entity relationship model. This is a huge time-saving win. It allows you to access data with several different models, such as key value stores, graph databases, columnar stores, document stores. Most, if not all, NoSQL systems leverage low-cost commodity processors that have separate RAM and disk. Right? They use a distributed shared nothing architecture. When you add more machines, they scale horizontally. And in a lot of cases, you get a consistent linear increase in performance. NoSQL systems also allow you to store your database on multiple processors, so you can also get vertical scaling with them. You typically extract data using a simple interface, which doesn't allow for complex queries. This brand new innovative technology was birthed in the early 2000s. So what were some of the technical drivers that led to the creation of NoSQL databases? There was a paradigm shift in the early 2000s. Businesses found value in rapidly capturing and analyzing large amounts of variable data, and then they would immediately make changes based upon that information that they received. So they were starting to react much more quickly than what they had in the past. So I want to introduce what I'm calling the 3 V's here: velocity, volume, and variability. Each of these drivers put pressure on existing systems, and they began to crack. As data volume increased, it forced folks to think about doing more and more work in parallel. This coupled with the fact that CPUs were hitting the power wall and their speeds were no longer doubling. This started pushing folks to think about scaling horizontally. The demands of websites increased the data velocity, right? This rapid increase in inserts and querying had to be dealt with. Existing systems really couldn't adequately handle the large bursts that would come in, and the net effect was response times had plummeted, right? Tuning these systems was really a nightmare. Businesses were discovering that not all customer data was created equal. Customers may have unique data that simply doesn't apply to the entire customer pool. The idea of shutting down a relational database to go perform a alter table type statement so you can add or remove some column, right? That really wasn't a great option because then you had downtime. So this variability led to improved ways of representing it. So a combination of the variability, the velocity, and the volume were all key drivers in what I want to call the NoSQL movement. Today's modern applications have a bunch of different characteristics. Applications are generating and ingesting large amounts of data at a very high speed. Think of IoT type applications for an example. Application response time is critical to match user expectation. For example, relevant recommendations on a shopping website, right? They need to show up fairly soon after a customer's click. With today's global, competitive, and dynamic business environment, enterprises expect innovations to happen rapidly to keep up with their users' demands and expectations. Applications demand a database management solution that can be deployed rapidly and is maintenance-free and is cost-effective. The application data models may change constantly and dynamically to meet the business challenges. They may include things like structured data, semi-structured data, or even unstructured data. Data models need to interoperate with one another. Today's applications are expected to be always on, 7/24. Customers expect a non-disruptive and fast service. On-demand scaling of compute resources is a must-have for different application workloads during different times. You know, think of any type of a shopping type of application, right? During certain seasons, you know, the amount of activity increases dramatically. Let's say during the Christmas season, and other times of the year, maybe it's not so much. Right? So businesses are looking to manage their operating costs by not over provisioning their compute services. With all of these characteristics and challenges, businesses are looking for a database management solution that will address them. So I have a couple of background slides on NoSQL, and what I have up here is this is a very interesting and fundamental way to think about this space. Eric Brewer wrote this paper in 2001 describing the notion of yield versus harvest. And this really centers around the idea that No matter how much time and energy you put into a system to make it perfect, it's gonna have some faults. It's unavoidable. Let me read it to you. Despite your best efforts, your system will experience enough faults that it will have to make a choice between reducing yield, i.e. stop answering requests, and reducing harvest, giving answers based upon incomplete data. This decision should be based on business requirements. So this is very interesting. You have to either stop answering requests, which you can think of this as another way of as basically blocking the system, you're reducing availability, or you have to provide answers with incomplete data, which is really nothing more than saying reduce consistency. Clearly, in some cases, you have to stop answering requests. Take a financial application, for example. But there's many other use cases where you can reduce harvest. And this particular trade-off is there on all database systems. The Brewer quote puts this trade-off in a very simple and easy to understand way. And his last sentence is very important. This trade-off has to be based on business requirements. Therefore, you have to understand your business requirements in depth. You have to know what you're looking to try to achieve. So going forward, there are many, many use cases where the trade-offs to reduce harvest is a no-brainer for these businesses. And kind of continuing with the background information, I'm sure that many of you are aware of ACID properties and what that means. And as we look at distributed shared nothing systems, most of them, if not all, really fall into that bucket, and they have to deal with a set of trade-offs. The original trade-off scenario was presented in a paper by Eric Brewer in 2000. And in that paper, he laid out what we commonly call the CAP theorem. In essence, this paper is about the choices you make in trading off availability for consistency, which really was referenced in the quote that we had just talked about. Then about a decade later, Daniel Abadi comes out with his paper, and it says it's not as simple as the availability or consistency trade-off. You have to consider the cost. And in this case, the cost is in terms of consistency. Is it possible to eventually converge on a consistent set of results after writes for multiple nodes in a cluster in a distributed system? Well, of course it is, right? But the question really is how long are you willing to wait for that to happen? Those trade-offs are described in the PAC-ECL algorithm, which builds upon the CAP theorem. So the PAC-ECL theorem states that in the case of a network partition P, in a distributed computer system, one has to choose between availability A and consistency C. And this is consistent with the CAP theorem. But this PAC-ECL theorem adds, but else, which is the E, even when the system is running normally in the absence of partitions, one has to choose between consistency C and latency L. So many of you on this call probably come from the relational world where ACID properties are strictly enforced. There are many use cases across numerous market segments where it's really not an option to talk about inconsistent data. We mentioned the financial sector before. With relational databases, consistency deals with bringing the data from one valid state to another based on a set of rules. However, I want to talk about several questions that come to mind, specifically when talking about NoSQL use cases, right? These all center around the notion of eventual consistency. And I'm going to pose a couple of questions that I would like each of you to think about during the rest of the talk. Does eventual consistency even make sense? Can people even pull this off? Think about your favorite retail site or your favorite streaming site. If you look at the landing page of your favorite retail site, can you tell if product recommendations are a little bit stale or out of date? Would you even care? What about the trending items? Same sort of question. If these are 30 minutes out of date, is that okay? What about an hour? What about 2 hours? Could you tell? Even if you could tell, Would you care? Let's say you're watching an episode in your favorite series, you hit pause. Then you pick it up, the rest of it, the remainder the next day. If it doesn't pick up exactly where you left off, do you care? If it starts back a little ways, would you go, oh, I'm just going to get rid of this service and go hunt for another? Do you immediately cancel the service? I would argue that you probably don't care. We all experience such things on our streaming sites. What would happen if you could get 100% consistent data? What if it could be perfect? Would you be willing to pay extra for that? Would you really be willing to pay a premium to your streaming provider that when you hit the pause button and you picked right back up again the next day, that you would start exactly where you left off? Finally, if you're using an app on your mobile device, how do you define it's not working? What does it doesn't work mean to you? If the spinner displays indefinitely, or if the app renders stale data, what would cause you to walk away from that app? I know for myself that if I get a lack of response on a consistent basis, that really causes me to think twice about the application. So after reviewing some of these questions, I hope you can see that there will be cases where close enough is going to be good enough. So let's dig into some of the specific use cases. So NoSQL databases are popular in many, many, many different markets. I'm going to cover a couple of examples in some of the remaining slides. I'm going to cover an example in healthcare, online retail, aviation, and entertainment. But we also see NoSQL in telcos, in manufacturing, marketing, gaming, IoT, financial services. A lot of times we see them being used in conjunction with relational databases. So let's jump into our first use case. You regularly hear about COVID testing in the media. In fact, I just had to go get a COVID test this past weekend myself. And this use case is very interesting because it really screams out that availability is far more important than consistency. And let me explain that in a little bit more detail. When you go in and you get your test, there are many places now where you're going to have access to consumer level notification events as things are moving through the process. And these events can include sort of what's going on with the sample. And what we have up here on the screen is we have several of the events where you have an appointment scheduled, and then you get notified when the appointment's completed. And then you got a couple of events dealing with the specimen. It was received in the lab, testing has started. And then finally you get a event when the results are released. And you can monitor these events on your mobile device. And then in a lot of cases, you'll get an SMS message with the final event, which happens, which basically says that, things were positive or negative. And that's really what you're looking for. Now, picture this and scaling this out for millions of consumers that are all wanting to get this kind of information. Think about what would happen if someone came up to you and asked you to build this thing. The requirements are it has to get rolled out quickly. It's got to be cost effective. You got to build it efficiently. And, thinking about the environment that we're currently under, right, it has to be consumer scalable. How would you solve this problem? What pieces would you use? How would you code it? I think a case could clearly be made that a combination of technologies could effectively solve this problem. Some of the data in this example you will want to persist possibly forever. And then some of this data is really what I'll call more temporal in nature. You can probably think of this app as using a customer ID as the primary key, right? And then these events that we just saw on the prior screen, right? All those events would be tied to this primary key, right? During the testing cycle, there were several intermediate events that arguably have a very short lifespan. maybe a week, maybe a couple of days, maybe 30 days. I mean, who knows? But I think I can say this with confidence that a year from now, are you really going to care that your appointment was completed? Do you need to save that? You know, that kind of information can eventually disappear. You know, and in this type of application for this type of data, you know, clearly you want to favor availability and latency for all of the customers doing the read access over consistency. Think about this. What would happen if you didn't get the message specimen received in the lab? Because when you did your read, you got stale data. I don't think you would have noticed that. You know, would you really care? You know, if you had a good buddy that got it and you didn't, would that cause you to drop the app? You know, while this kind of information is really nice to have, it probably isn't a must to have. You know, this is a great example of where you need availability, but not necessarily consistency. You know, and then in this larger app, right, you need a full-featured relational database to hold things like the HIPAA data, patient data, the final test results, contact tracing data, and other sensitive data that you're going to want to keep around for regulatory reasons. Full asset properties would be very important. You may need to do analytic reporting on this data, right? So this is a great use case where you have the need to cost effectively scale out, and then along with it, you need a relational database to handle the regulatory requirements. And what's interesting about this use case, right, is it is absolutely relevant today as we speak. And these types of applications are getting developed across the US. So let's move on to our next use case. And this one is all about online retail. And it's really would be hard to imagine that any of you out there don't use online retail. Right? All the major retailers have an online presence. Walmart, Target, Amazon, you know, your grocery stores, Safeway, Kroger, what have you, right? And when you bring up a homepage, it's typically customized for you and not for anyone else. They have monitored your past browsing behavior and have customized a home screen tailored to what you order and what you look at. Oftentimes you'll see product recommendations. You're usually one click away from reordering what you ordered in the past. You know, there is information on topics based upon things you looked at before. There's all kinds of history information, billing history, return history, order history. A lot of times that type of information is fully searchable. And I'll ask you, would you notice if anything was out of date in terms of recommendations or one-click order items, or if something was missing from a past order, or, you know, if it took about a half a second to pop up some type of a product recommendation? You know, think to yourself, what would you expect from such a site? And looking at this page that we have on the screen, there's even an ad that is being served up, most likely from some past browser behavior, right? Again, close enough is good enough with respect to the ad. We want to serve up an ad, and we probably don't care how recently the data came from to figure out which ad to serve up. You know, and actually rendering ads is another great use case. I don't have any slides on it today, so we'll have to cover that another day. So let's take a look at a real-world example of brewer's choice in action. So do we reduce yield or do we reduce harvest? So back in 2010, Walmart Labs, and that's the technical side of Walmart, they decided to re-architect their back-end systems. They were faced with the brewer choice. And on the left-hand side of the screen, this is where we see it all came to an head. In an entire region, Walmart Canada was unavailable. Their yield went to 0. So what was the effect of this? Customers were frustrated. Customers gave up. Customers went shopping elsewhere. Customers complained. Customers got no response. And when we think about this, you know, I'm sure this is not the message that Walmart wanted to send to its customers. So they wound up shifting their model to reducing harvest. So outside of the programming changes they needed to do to focus more on reactive principles and changing their platform schemes, right? They introduced microservices, and at the core of the microservices was they shifted to eventual consistency. They realized that it was much better to reduce harvest and not to reduce yield. So how would you build it? What if someone came to you and asked you to build Walmart.com? What would you use? What would be the building blocks? How would you handle the trade-offs? As demonstrated in the prior slide, right? Brewer's yield versus harvest principle came into play. We see this notion here again that both NoSQL and relational databases have a position in the solution. They both can work hand in hand to deliver the totality of the business requirements. NoSQL clearly can work in certain parts of the business where consistency can be reduced. You're never going to know or care in some of these cases if you're not 100% consistent. Think about it. Product recommendations, reviews, trending items, right? Those do not need to be 100% consistent, but they do need to be available. User convenience functions like auto expiry of data is very important. Why take up disk storage for recommendations that have essentially expired? What if you can't get the product anymore? On the relational side, you need a strong asset database with rich reporting, right? There's going to be an order management system involved here as the underpinning of everything. You need to accurately keep track of inventory. You will report these numbers if you're a public company, and you're going to have SOX compliance. Senior executives at your company will sign off on this, and there's no way they're going to want to base their decisions on stale data. And as you can see, both the NoSQL and the relational database play an important role in this application working together. Here is another use case, and this particular use case comes to us from Emirates Airlines. And we had a bunch of discussions with them about 6 to 8 months ago. And when we thought about this for a little bit, we all realized on the team that this was a perfect use case for NoSQL. Many airlines like United, Delta, American, Qantas, right? They're all starting to offer real-time baggage tracking. What you have to do is install their app. Once you install their app, then you can get close to a real-time feed of where your bag is as it moves along its journey from source to destination. So ask yourself, would you be willing to pay extra for this functionality? Probably not, right? This is a real good example of offloading queries from what we would have traditionally called the operational data store. In the Emirates case, this data was already stored in their operational database. But what they didn't want to do was they didn't want to put these consumer level queries on that data store. So they needed an alternative. The second thing in this use case is the involvement of what we call the active-active piece, where you need to write to local data centers as the bag travels along. Clearly, for the best latency, you want the RFID bag scans to be immediately written to the local data center, and then you can let the database system take care of propagating that data to other data centers in an active-active setup. If you took a trip from the US to Europe, for example, right, the last thing I think you would want is to have all of these bag tag updates occur back to some data center in the US. Think about it. There's hundreds of bags on a given flight segment that get scanned. And you're going to want the best possible latency as these bags are moving from step to step, so they can be processed along. So a similar theme emerges here. You want to offer predictable, low latency and availability over strong consistency for parts of your data. So one of the things that we see in this use case, as I mentioned before, is we're offloading consumer level queries from the operational data store. We really have no way to predict what the load will be of these consumer level queries. However, we certainly don't want to hinder our operational data store or endanger our back office in any way. After you're done with your trip, you probably do not care about your baggage tracking data for that journey. The auto expiry is a very nice developer convenience function that can be used to remove this data after a couple of days. Maybe you want it for a few weeks, maybe a few months, just so you can run your reporting. But eventually you want this data aged out. You want it gone, and it's nice that this happens automatically for you. We also need a strong asset database for the system of record, for the operational analysis, for rich reporting. You'll need to do analysis on things like, how long does it take to process all the bags from a flight? What's the average number of bags per flight? What percentage of the flights are on time? What percentage of the time did we lose someone's bag? What was the cost of losing these bags, right? This types of information you'll be able to get out of the relational database. So what we have next is we developed a real-time baggage tracking demo, and I pre-recorded it. That way, hopefully I wouldn't have any technical difficulties. So I'm going to go ahead and play that now.
What I want to show everyone now is a recording of running through an application that we developed on the team, and it's a real-time baggage tracking demo. And so you go to it by heading toward ndcsdemo.com, and I will do that here. And when the home screen pops up, you get our little airways, the blue mist airways. And what we're trying to do here is kind of show you a real-time baggage tracking demo. And this demo is based upon many of the components that are in the Oracle Cloud infrastructure. So namely, it includes the Oracle NoSQL Database Cloud Service. That is the backend data store. It includes the OCI API gateway. The purpose of the gateway is it isolates the UI from the REST server, and it really allows for easy orchestration of REST servers without affecting the UI. We also have the OCI geosteering traffic management component. This steers network requests based upon application supplied routing rules. And in addition, it allows applications to easily offer worldwide application functionality with awesome local user experience. And really what's happening behind the scenes here is that you specify which region a user will be steered to based upon their location. And then finally, we use the Visual Builder Cloud Service, and this is used for all of the UI development. So when the home screen comes up, you get the blue mist airways. There's 3 different buttons there. There's the book tickets, change flight status, and track your baggage. The only one that we have implemented so far is the track your baggage. So I'm going to go ahead and click on that. And when you click on that, you get a random user, in this case, Lindsay Ferry, and we get the baggages that were tracked on her trip. So you get the flight number, you get the destination, you get the fact that this person arrived. And if I scroll down a little bit, I see the various stages along the way where the bags went from. So here there were two segments to this particular journey: Los Angeles to Taiwan, and then from Taiwan to Ho Chi Minh City. And then we have the timestamps of when the bags were scanned along the way in the console. And so you can see everything as this is going along. Then if you go up to the top right and you hit the hamburger button, and we'll do that here, then you can hit track your bag again. And then it will produce another random user, and you can look at that one. This one is Felicia Look. We have her flight number. Her destination is Madrid. Again, we will scroll down. This particular case, there's only one segment in her journey going from Los Angeles to Madrid. And again, we can see the timestamps there off to the right and where the bag basically traversed along its journey. So although this is a rather simple implementation of a baggage tracking system, right? It integrates many of the OCI services that are available on the Oracle Cloud Network. And as I said in the beginning, the basis of all this is using the Oracle NoSQL Database cloud service. So next, what I want to do is to show you a few more slides of some of the backend architecture and what some of the records look like.
All right, so we got this data from Emirates, and we sanitized it, and we added some randomly generated data. This is a reasonably complex JSON structure with arrays and nested documents. We also have arrays within arrays. And this forms the basis for the information that you need to track someone's bag, right? So we have their name, we have the ticket number, then we have an array of bags, because certainly someone could have more than one piece of luggage that they're traveling with. And then for each associated piece of luggage, right, we have the various flight segments, and when they pass through the various RFID scanners as that was moved along. And then I had promised a overview slide on the reference architecture. So on the left-hand side, we have, the mobile applications making queries. We have a websites making queries, which goes through a global DNS that then gets put through the geo steering component. And the geo steering component will take a look at the device's location. And based upon that, it will route the request to the appropriate OCI region. The Oracle NoSQL Database Cloud Service is active in 22 different regions worldwide. So depending upon where you're making the request from, then that will get routed to the appropriate region. And then we have this deployed today in each of the regions, the 22 different regions. And then for the individual deployment, there's a Apache web server, which then sends requests to a OCI API gateway that then goes through a Tomcat server. The Tomcat server then issues various REST requests to the NoSQL backend, and then responses are sent back through the system. So let's move on to our final use case. And this is another interesting use case. As a society, we are probably at a crossroads with the way entertainment is delivered. When I think back to when I was a kid, I think what I had for television was basically the big three networks. I had ABC, NBC, and CBS. Then as we moved into the 70s, I think PBS came into the market. In the 80s, Fox Broadcasting came into the market. And while I had choices, in reality, those choices were pretty limited. right? Everyone received their content really from one of those various networks. So let's fast forward to today, some 40 years later. We now have a totally different way that content is delivered. It's through mostly what we call streaming services. We have services like Apple TV, we have Hulu, we have Netflix, we have Amazon Prime, we have Sundance Now, we have Peacock streaming. It is very possible that some of the major networks will become streaming services like so many others. People today are really used to consuming their entertainment content through these streaming services. Many of these in the past were at one point in time technology providers. Think of Apple, Amazon, Netflix, right? But they've all shifted their focus to streaming. These platforms that they developed, right, have now essentially become commodity items. Really, the bottom line is this. This is a huge market segment where when you think about it, close enough is good enough. And if you think about your streaming experience, really what these platforms do is they're really persistent session management, right? They're keeping track of things like what episodes did I watch? How far along in those episodes did I watch them? They remember things like, did I have subtitles turned on? What was the streaming rate? Did I have closed captioning turned on? What was the playback quality? Was it 480? Was it 720? Was it 1080? Right? And really, we can think about all this stuff as being actually pretty simple in nature. And all of this stuff really falls into this larger bucket that I want to call metadata. And even though this data is simple, think about it in the context of millions or even tens of millions of consumers, right? This is a lot of volume of data. So let's go back to our core set of questions. How would you build this? What would you look at? How do you make it cost effective? How would you make it scale? How are you going to add all of these features, right? With the number of players in the market, you're not going to be able to charge extra for this stuff. All the streaming services really have a very similar level of functionality if you go back and you look at the different ones, right? Basically, it works like this. You pay a base monthly price, and then you get all of this rich functionality. This is another case where you want to combine the power of both database technologies. You will need a strong ACID compliant database for your order management and your billing system. In addition, you're going to need the ability to do rich reporting. So all of this will go into your RDBMS. All the other stuff that's really not critical, like when did I hit pause, what episode did I last watch, can go into a NoSQL database that can cost effectively handle the session management for all of your customers. You can easily scale this out horizontally as your customer base grows. This is a case where you clearly want to favor availability over consistency. When you think about it, probably no one really cares that this data is a little bit stale or a little bit out of date. We covered several trade-offs in the context of the use cases. Some of them we talked about more than others. So I want to talk about, some different trade-offs as well as reiterate some of the ones that we already discussed. So the relational model is attributed to Edgar Codd, who developed it in 1970, right? The tables each contain columns representing predefined data types, which contain unique instances of data in what we traditionally call rows. Relational databases generally use structured query language, or SQL, which is really nothing more than a programming language designed to work with rationally organized and fixed tables. NoSQL management systems, on the other hand, really emerged directly from the need for web companies to ingest, store, and process volumes of growing data in a flexible manner, right? Driven by new technology needs, giants such as Google, Amazon, Yahoo, Facebook, they all needed a better way to ingest and store large volumes of data. NoSQL databases were created to solve that need, where access is mostly done via primary key, and you have an opaque string of data that oftentimes the database doesn't even know how to interpret it. So you have this technology from the 70s, which has been around quite a long time, over 50 years now, and then you have this sort of rather infant technology on the NoSQL side, which has been around about 20 years. With the relational world, it brings in a strong notion of ACID and strong consistency. This creates a trustworthiness of operational data needed for your back office. You know in advance the exact structure of the data, and you know how that data is going to interact with other data. However, with a NoSQL database, you get the agility in schema design. You get tremendous flexibility. You get extremely low latencies. This equates to less design time and a performance-focused engine. In the traditional RDBMS, DBAs are always present. They handle things like design and redesign, monitoring, security, backup and restore, access control, and a whole host of other activities. Folks have spent their entire careers as a DBA, right? Well, under the NoSQL world, right, we could say that the developer rules the roost, so to speak. JSON objects contain a built-in schema. There isn't the need for this extensive upfront design. While backup and restore and security, right, those are still present, but they're often handled via some form of an API. So this traditional DBA role is almost non-existent. Because RDBMSs are designed for structured data requiring precision and accuracy through adherence to ACID principles, they work extremely well when you have business requirements that need those type of attributes. With this model, you can easily scale vertically by adding CPUs or memory or disks. But in the relational world, it's much more difficult to scale horizontally. NoSQL databases, on the other hand, were designed from the ground up to work in a shared nothing distributed architecture. They excel at scaling horizontally. Finally, relational databases have the muscle to handle complex queries. Complex queries involve different levels of joins, subqueries, heavy use of conjunctions and disjunctions. And really, to the uneducated, a large SQL query can look like a gigantic tangled mess to somebody. NoSQL databases, on the other hand, they offer up flexibility to handle structured, semi-structured, and unstructured data. You have document stores, graph stores, key value stores, column-oriented stores. Some NoSQL databases allow you to have multiple models within the same database. This gives you extreme flexibility, adaptability, and changeability. Gone are the days when you have to develop a complex entity relationship model and put everything in third normal form. So, coming around the final bend, we have some common themes here. Number one, many of use cases favor availability over strong consistency. Like we said in the very, very beginning, none of these use cases deal with transferring money from account A to account B. No one would want their banking application to run on a system that does not offer strong consistency. There are many use cases, however, where close enough is good enough. We covered a few of those in this presentation, but there's lots more that we could have covered. Another thing is people just expect certain levels of service today. In the entertainment world, with access in mobile application and others, people expect functionality to be there, and you can't charge a premium for it. As a result, you need a cost-effective scale-out solution. Customers want a system that is predictable, scalable, and most importantly, available. As your customers increase, you have to be able to easily scale the data store. Now, in a lot of the cases, the majority of the accesses are done via primary key operations. For instance, a customer ID, a ticket number. However, there are cases where you may need some non-primary key oriented operations. Think about the retail case, right? And I want to look at my order history, and I want to go, oh, how many times in the past did I order this particular item, right? So you would want some type of non-primary key query to happen. So we've seen this also an emergence of customers wanting data that would normally be in the back office. We only expect this to increase. Everybody wants everything available on the mobile app, and they want it now. This is creeping into many market segments, including banking. For example, the ability to apply for a loan using your mobile app without the need to go into a bank. Right? We're seeing more and more banks starting to offer this type of functionality. At one point in time, all of this stuff was in the back office, and it's now being made front and center on mobile applications to consumers. Then there's this notion of convenience functions. We talked about auto expiry of data, and we talked about active tables, and there's many others that NoSQL databases can offer. So I wanted to kind of offer some contact information. So this slide covers a couple of key folks on the team. We have the product management team, we got the product marketing team, we have contact information for the development team. We have 2 websites. We have our product page and we have our technology page. On the product page, we have all kinds of information about the Oracle NoSQL Database Cloud Service. On the technology page, we have information about our on-premise version of the product, as well as a bunch of other stuff. There's videos, FAQs, all kinds of additional information out there. We have a blog, and there's the URL to the blog. There's lots of different blogs out there covering a wide range of information. And as part of listening to this talk, we are offering a way to try the NoSQL Database Cloud Service now. On this particular slide, what we're offering here on this trial, as long as you sign up before, I believe it's February 26th, we're offering $500 in cloud credits that you can utilize. If you miss the February 26th window and you do this after that, then there's only $300 in cloud credits that you'll be able to use. And then a big thank you from myself and Kieran, as well as Dave, who worked together to put this presentation together. And I think we have a little bit of time left that we can open things up for questions if there are any.
Hi, Michael. I have a question here. One of the questions is where all the NoSQL Cloud Service available in the Oracle Public Cloud regions?
Yeah, so the Oracle NoSQL Database Cloud Service is available in 22 different regions worldwide. We have regions in all of the continents. I don't want to go down the list of all 22 of them, but we have them in Ashburn, we have them in Phoenix, we have them in London, we have them in Dubai, We have them in Mumbai. We have them in Tokyo. So we really have them all over the world.
Excellent. Another question I have here is the latency times. Can you elaborate on what type of latencies can you expect?
Yeah, so we've designed our cloud service from the ground up to be highly performant. And we are constantly doing measurements against our cloud service on the, what's the latency for the reads and what's the latency for the writes. For both of those, we are in the single-digit millisecond range. Our reads tend to be in the 3 to 5 millisecond range, and our writes tend to be in the 6 to 8 millisecond range. And we put a lot of time and energy within the development team to make sure that we're putting out a very highly performant product.
Excellent. Another question I see here is, does the NoSQL cloud service support REST APIs?
So we offer a wide variety of ways to access the cloud service. We have a series of language SDKs in, we got Java, Python, Node, Go. We have a Spring driver. All of those are hosted on GitHub, and with an easy search, you can go find them on GitHub. In addition to that, we have a OCI REST interface that is available in our documentation. You can get access to that. The REST interface primarily provides basically get and put types of REST interfaces. Our SDKs provide a much richer experience and accessibility to a broader range of APIs and functionality. So, unless you're specifically looking for a REST interface, which is available, we like to direct people to the various language APIs because of the richer functionality that they provide. All right, I think we're at the top of the hour, unless there's one final question that is coming in. But I want to thank everyone for taking the time to join in the presentation and to learn about NoSQL databases.
Thanks, Mike and Kieran. I just wanted to mention that we did record this session, and we will make the recording and the slide deck available in the next couple of days. You will receive an email with the link. So just wanted to let you know that. So thank you for taking the time to spend your hour with us, and we hope you have a great day.